Hello everyone, good morning. My name is Ladia and I represent Liquid Protocol. I'm the CEO and founder of the startup. We have an international team with members from India, the UAE, Canada and the US. And in addition to our product developments, we also have a research wing where we try to figure out some new cutting edge use cases of blockchain. And this is one of them. And as you can see, it is privacy-centric collaborative machine learning model training via blockchain. Now the title sounds very long, but I'll try and demystify it for you. So let's start with a small insight. Today, machine learning is a rather popular form of data analysis. It's used in a variety of industries, and there is a lot of research work going on regarding machine learning. One class of machine learning that is particularly popular, and those of you here who are interested in AI and probably work on it would know, is supervised learning. And the way supervised learning works is essentially you create a computer program, which data scientists call a model. You feed it data sets. So these are data sets that have already been established. You may have 2 or more variables, and these are typically taken from the real world. So you feed them these data points, and you let the model do its magic. So what does the model do? Well, simplistically, it produces an algorithmic expression that correlates the variables in the data that you provide. This is one particular type of machine learning models. And then the advantage with these models is that you can give it new data sets that are incomplete, data sets that you want to predict. And the machine learning model, with a certain degree of accuracy, outputs these predictions. Now, as you can see from my explanation, which is rather simplistic, but if you know about machine learning, you'll definitely know about this. Machine learning, and in particular supervised learning, depends heavily on the quantity and the quality of data that you provide. So if you provide largest data sets, which are of better quality, the predictions made by these machine learning models are likely to be better. Now, with my experience in the industry, working with banks, working with governments, I've come to realize that the problem isn't that we don't have enough data. The truth is we have more than enough data. The problem lies in the fact that this data is scattered. So we have so many companies, so many organizations, so many governments, and all this really useful data is fragmented among them. So I hold a certain part of the data, you hold a certain part of the data, 1,000 other people hold a certain part of the data. And when I make my machine learning model, unfortunately today, I'm forced to train my model only on my data or data that is publicly available. But I want you to imagine for a second, if I could train my model on all the data that you guys have, how much better our models could be. Now this is the central premise that my solution aims to target, which is collaborating for machine learning models. And presently, the biggest obstruction to this collaboration is regulations. So just about last year around this time, we had the European Union adopt the GDPR. I'm sure all of you know about it. And the problem with these regulations is that they disincentivize data sharing. Why? Because in case data is stolen or in case data is leaked, the consequences are simply far too high. And me as a company or as an organization, I don't want to take those risks. So even if I wanted to collaborate with another company for machine learning, collaborative machine learning training, I feel forced not to do so, just because in case something goes wrong, in case data is stolen, the consequences are very, very heavy. So I think I don't really need to explain further, but I'll still go on to it. Why is it that we need data sharing? So my first point is about accuracy, and this is the trivial point. Most of us would know about this. If we can give our models higher quality data sets, their predictions are likely to be more accurate. And mind you, even a 1% increase in the accuracy of models could save millions of dollars could make life much more easier for consumers and businesses. So even a slight improvement is an improvement worth looking out for. The second advantage I see is that of automating more tasks. So today we have a certain group of tasks that machine learning models are commonly applied to. Banking, predictions. But there are a lot many more where we can put in machine learning models, but because we don't have enough data, there's no point, pursuing them. But again, I want to correct myself. The problem isn't that we don't have enough data. The problem is that this data is scattered. And here's where I'll introduce the first term for today, what I like to call data silos. Data silos are independent stores of data. So if there are 5 companies, each company has their own data silo. And the problem with these data silos is that they cannot talk between each other. So the data in one stays in one and is accessible only to the company who owns it. They don't talk. They're completely isolated. So keep that terminology in mind. It'll be used again and again in my explanation of this paper. But lastly, and perhaps the most important benefit, is to do with society. At the end of the day, as data scientists, as people engaged in blockchain and AI, our endeavor is to improve lives, to make things better, more automated, reduce the burden on consumers and businesses. Now just imagine, and I will cover this later on, today if a cancer prediction model can be maybe 0.1% more accurate, how many lives can it save? Or imagine today if the police used machine learning models and they could catch criminals better, how many people here in this room would feel more secure? Those are the benefits that I'm really looking out for. And hopefully with collaborative machine learning models, we can reach towards such solutions. So I think now is the time that we really define the problem statement for this paper. The problem is that organizations should be able to share data for machine learning in a completely privacy-centric way, which means that data owned by one particular organization should never be revealed to anyone else but the data owner. And there's a small asterisk to that, the terms and conditions, third parties. So currently we need third parties to do this. We both give our data to a third party who performs some sort of training operation. But as we've seen with scandals like the Facebook Cambridge Analytica, third parties aren't always trustworthy. And with millions of dollars in fines, we can't have third parties in our solution. So my paper aims to take this problem statement of ours and offer one solution in the direction. Which brings me to the contributions of my paper. And what I summarize here is essentially the goals of the paper, what the paper presents. And at this point, some stuff might seem abstract. But as we go on and as I explain each part bit by bit, things will hopefully start to get clearer. So, the contribution is to present a blockchain-based system that A, ensures that data is never transferred and is never visible to any party other than the owner of the data, and B, there is a transparent audit mechanism to identify any instance where data may be leaked or misused by any party. And this paper is broken down into 3 main sections, each technical in its own light with applications. So first we have an access control mechanism. As we'll see later, the crux of the solution depends upon a blockchain-based access control mechanism to a computer that I call the training machine. Now I'll be defining these terms in the slides to come, but just keep in mind that we are presenting a blockchain-based access control system. Secondly, we are offering privacy protections. How do we ensure that the transactions that we conduct over this blockchain network of ours are privacy-centric? How do we ensure that data is never misused? And third, but not the least, we have a proof of concept, an implementation that indicates the capabilities of this model at a smaller scale. So let me define define the scope of this problem, or rather the scope of this solution. This solution is meant for consortiums. Consortiums are groups of companies or organizations within one industry. So many of you would know about the R3 consortium of banks, which is really, really pushing forward for blockchain adoption. But any sort of consortium in any industry can make use of this solution. And, Right. And the method in which, consortiums can make use of this solution hinges upon a space, or more technically, a container, where machine learning can take place, whilst ensuring that this container is not visible to any party. So think about it like a black box. You give it an untrained model, you throw in the data, it does something to the data, produces the trained model, and deletes everything else. And this container that we have should not be accessible to anyone. So nobody should be able to open the container and extract any data from it. It should all function in a completely isolated, privacy-centric way. And I call this container the training machine. So what is the training machine in a slightly more concrete form? Well, it's essentially an array of computers. So think about a system of computers that a consortium buys together and sets up jointly for the sake of machine learning. And we'll explore how this container can be set up and how this container can ensure that data is trained in a privacy-centric way. So I think this slide sort of encapsulates the 5 very high-level processes that my training container follows. So it takes in the data, it takes in an untrained model, trains the model on the data, returns the model, and deletes any data sets that were used in the first place. If you would take a slightly more technical overview of that, we have our training machine out here, which is the secure container. We have individual parties supplying the untrained model and the data sets to it. And the output of this training machine is the trained model, which is returned to the owner. And any data sets that were consumed in the process are automatically deleted. So what are the components of the system? I already defined the training machine for you, but there are 3 other components that are key to the operation of this system. So first of all, we have our data control chain. And this is just the name of a blockchain that operates amongst the members of the consortium. So let's say there are n members of a consortium. All of them have peers to this blockchain network called the data control chain. Next, the second component is the ledger bridge. And the ledger bridge is simply a piece of software, a piece of code that resides on the training machine. And the ledger bridge is the only link between this isolated container called the training machine and any human interference. So what it can do is it can read commands, or it can read changes to the state of the DCC. So it is also a member of the DCC. It can read changes to the state of the DCC, and it can execute commands on the training machine. So it's essentially an interface between our data control blockchain and the training machine. And lastly, we have private channels. So now this is very specific to Hyperledger-based systems, but essentially what private channels are, they are sub-blockchains, mini blockchains between specific members of a consortium. So let's say there are 50 members of a consortium, but only 5 want to take part in some sort of a collaborative model training operation. They can create their own blockchain, a sub-chain, or more likely, a private channel for it. So that's what a private channel is. And these are the 3 main components of my system, in addition to the training machine. Now this is really the crux of how the system operates, and I'm going to take some time to run you through the entire steps of this procedure. So before we go for this, let's just recap. We have our training machine set up. We have a consortium of n organizations. We have our training machine set up by these consortiums in some physical location pre-decided by them. Note that nobody can control the training machine directly. These details are presented in the paper, and you could definitely have a look at how that's accomplished. But with this sort of an establishment in mind, let's take an example where out of these N members of the consortium, 3 of them, companies A, B, and C, want to take part in some sort of a model training operation. So company A has created a model, and companies B and C are ready to supply their data to train this model, provided it's done in a privacy-centric way. So first, of course, we have our off-chain agreement. And this is your regular legal papers, the formalities, all common stuff, so we won't delve into that. But what these guys do, once they've agreed upon it in a legal sense, is they create a private channel. And this private channel has only these 3 parties on it, A, B, and C. A channel is separate from the DCC, so members that are not on the private channel can't see what's going on there. But at the same time, each private channel is identified by what's called a name or an identifier. So with this in mind, the company A, which after all has created the model, what it does is it sends a proposal on the DCC. DCC being the main chain where all the consortium members are part of. So it sends a training request on the DCC, and what this request consists of course, it runs as a smart contract or a chain code, but essentially it specifies the identifier of this private channel where these 3 companies are a part of. With this chain code being executed, the purpose is essentially to check whether the training machine is currently occupied. So there may already be some sort of a model training operation going on the training machine. And if that is the case, currently we don't allow for parallel operations. If that is the case, the proposal is rejected. But if not, if there's nothing going on the training machine and it's free to take in a new task, the proposal passes. And when it does, the state of the ledger is updated to reflect the identifier of this private channel where these companies are a part of. Now, with that in mind, the ledger bridge, which is operating on the training machine, it recognizes this change in state and it joins this private channel. So now the private channel has our 3 companies, A, B, and C, and it has this 4th component to it, which is the ledger bridge, which of course is residing on the training machine. So for practical purposes, we can say that the training machine is now a part of this private channel. And now, what happens henceforth is quite intuitive if you think about it. First, parties B and C, which have the data, these guys share the locations of their individual data sets to our training machine over the blockchain. Now, there are a number of ways to go about this in a privacy-centric fashion, but one way is to make use of snarks, ZK snarks. I would refer to Zcash here, which allows you to transact between parties and verify those transactions without really specifying how much of an amount is being transferred and from which party to whom. But there are a variety of ways to do this other than snarks as well. So these locations which are on independent servers, so party B has its data on its own servers and party C has its data on its own independent servers, and both these parties send a transaction across the blockchain, across the private channel to our training machine specifying these locations. Now again, just because we've added blockchain, that doesn't mean that we discount the importance of existing systems like public key infrastructure. So they can be set up to only accept requests from the training machine. That's all up to the members of the consortium. Now with that done, the party A, which has created its model, also does a similar thing, essentially specifying where its model is located. The training machine fetches both the data and the model. And once that's done, the data transfer operation is more or less complete. Now, if we pause here and have a look at what just happened, we have this container, this training machine. Nobody can make use of it, so nobody can just SSH into it and start typing up commands because it doesn't accept any commands remotely. It only accepts commands that are issued through the ledger bridge. And this training machine has fetched data and models from independent locations. And essentially, we fill this black box up with all the components that we need to train a model and the data sets. Once that's done, the training machine can start its training operation. In our proof of concept implementation, we tried using TensorFlow, and we just ran a couple of models from public data sets. So we took public data sets and we split them up into 4 or 5 parts to represent data sets that are held by individual entities, and we ran this sort of a network. So it runs, it starts the training, and once the training is complete, we come to our conclusion stage, where essentially the data is cleared, so all the data that was collected is permanently deleted from the training machine. This is posted on the DCC, so a confirmation is posted to indicate that yes, all the data has been deleted. And the final model that has been trained is returned directly back to party A's servers. And with that done, the state of the training machine is again updated on the DCC to reflect that it's unoccupied and willing to accept new jobs. So that is more or less the high-level overview of how this system operates from a functional standpoint. So what we did here, if you noticed, is that we integrated centralized processing with decentralized access control. So initially our thoughts were, is there a way we could do this entirely on the blockchain and exclude the training machine or a centralized area where training takes place altogether? But what we concluded was that currently that's either too expensive, too slow, or just inefficient. Because blockchains aren't meant to compute large sets of data. They're meant to transfer information, transactions, and so on and so forth. So we sort of took that approach and we applied it to this problem out here. Now we also added another provision to our system by extension. So we kind of realized that machine learning models, training of these models is not entirely automated. You need to maintain the models occasionally. You need to see the progress that's been done. And so this is sort of the beta stage that we've tried to put in. And it allows the training operation, the trainer, so entity A in this case, to have a look, to sort of get limited access to this training machine and monitor the progress with data training. So what this means essentially is that another access proposal is created by entity A, which has the need for privileges, the access time, and the purpose. Once it's passed, it's approved, a call is made to the ledger bridge, and a limited user profile is created on the training machine. So this user profile does not have sudo rights, does not have admin rights, simply inspection rights. And with that in mind, the SSH keys are updated so that organization A can sort of SSH into it. In our instance, of course, you can make use of any remote communication protocol. And any changes that are made to the bridge or to the training machine at that point are automatically logged for audit. So they're automatically published onto the DCC for audit purposes to ensure that nothing wrong is going on out there. And eventually, once the access time expires, the access is revoked and we start our whole process once again. So we did perform a bit of a risk analysis on this, and I think we identified 4 main places where things could potentially go wrong. First of all, we could have the chance of majority of nodes being compromised, a 51% attack, common to all blockchains. But of course, we're assuming that this is an enterprise environment, so the probability of this happening is fairly low. Data fetch operation compromised, so if there was some way in which, while the data was being fetched, some adversary could intercept and sort of capture this data. But again, we aren't changing anything here. We're making use of pre-established secure file transfer protocols. So in case there is a bug with that, well, it's not really our system, it's the protocol that would be at fault. And so far, it's proved to work pretty well. Third, of course, which I think is probably the biggest area of work out here, is in case the ledger bridge itself is compromised. So that is, I think, the weak link in this whole system, because that is a piece of code that we write that connects a decentralized system to a centralized processing unit. So we need to make sure that that's robust. But of course, as far as we are concerned, we've done our best to make it as secure as possible, and we look forward to researchers sort of building up on that and making it more and more secure. And lastly, we have malicious code in the ML model or in the training data, which to some degree requires a bit of trust on consortium members. But beyond that, there are a variety of methods to check for any malicious, lines of code within the data and within the model that's fetched. So overall, we gave it a risk assessment rating of 5 on 25, and it's broken up as follows, with a 1.5 for likelihood and a 3.5 for severity, putting us somewhere in the green zone. And if we correlate that, that basically links to acceptable and some sort of monitoring of the system on a day-to-day basis. Now, quickly, I want to run you through, a few applications for this that we worked on with our industry players and as a team. So we have a chain of benefits for the insurance sector set up here. So first of all, we have more accurate predictions because, as you know, insurance depends on identifying how risky a consumer is. What that means is that consumers get savings. Providers get savings. So if you have a more accurate risk analysis, you get a better estimate of the premium you need to charge to a customer, and that reduces risk on part of the providers. And also, any savings that are done in this process can be passed on to consumers. So if you're a safe consumer, your premium could fall down. That's the benefit that we sort of identified here. We have another one for governments, and we've been working with a couple of state governments within India, and also trying to figure out a partnership with the government of Dubai. And since governments are some of the largest stores of data, they have data on citizens regarding their healthcare, regarding their lifestyles, all of that. If we could have some sort of collaboration between them in terms of police, in terms of finance, in terms of healthcare, well, we could have a whole host of benefits, which I think is quite self-explanatory. We also had a look at healthcare. So if labs, for instance, could create untrained models, which they already use, and if they could make use of data from other parties to train their model and get more accurate predictions, well, that could be something that could be very useful. As I mentioned before, imagine the number of lives a more accurate cancer predictions model could potentially save, especially considering that we have this data, but just that we're not able to share it amongst each other. So lastly, we have a couple of limitations for this right now at this stage at our proof of implementation. Maintenance of TM, the training machine, is presently manual, so it requires consortium members to physically be on the site. It requires them to sort of sit together and do any maintenance tasks that need to be performed. Only limited access rights are provided over the DCC, which I said were just for viewing and for maintenance purposes at a very small scale. Admin rights are currently not supported. And current implementations right now support a limited pool of platforms for machine learning training. But of course, this is just a proof of concept, and scalability is something that I expect the community to take forward. And as my last slide, I'd like to acknowledge the role of two major companies here that I think were instrumental in developing this research report. So we have Emirates NBD, the National Bank of Dubai, the biggest bank of the Middle East. And we have a couple of people there, Mr. Nemish Shah, Mr. Evgeny Makarov, and Mr. Akshay Meher, who all worked with us to sort of figure out industry use cases and refine our technical knowledge on this. And I would also like to thank Mr. Tanveer Shah, who is a partnership consultant in Dubai, and he helped us to meet with clients and see whether this solution could actually work out. So a big thank you to both these players, and I hope you like and enjoy my papers. I'm open to any question.
Thank you, Aman. You have used